Yes, sir. Yes, sir.
You can see the screen. Fine. Okay. Okay. Okay then. Yeah. Okay. So today I will talk about pyridine, and in this chapter, pyridine, quinoline, isoquinoline, and some derivatives of pyridine. So pyridine already. Yeah, I told you the what is pyridine and all the things. Some elaborate discussion on the aromaticity of pyridine. And in case of pyridine, I'm again just remind you or recap you. This is pyridine. Just one carbon of benzene is replaced by nitrogen, and that makes lots of different properties. I explained that why, because nitrogen has a lone pair of electron, so it's basic. And also the characteristic, I mean the reactivity of benzene compared to pyridine is different. It's electron deficient, benzene is electron rich. Because all the electrons in the ring are attracted by this nitrogen, electronegative nitrogen. So overall effect is that the ring is electron deficient. Okay. Now I will talk about the synthesis, reactivity, everything. And I will go slow so that you can understand. I have enough time, no problem. But the only thing I'm worried about is your understanding. You try to understand, try to again, I'm telling you the same thing, try to understand the chemistry. The Hans pyridine synthesis, that's one of the classical method for synthesis of pyridine. And that's very simple. That one is two molecules of beta dicarbonyl compound, that is beta dicarbonyl compound, an aldehyde, and an ammonia. It's called a multi-component reaction. If it is, I repeat it again, if it is more than two, we can say three-component or multi-component reaction. And so ethyl acetoacetate liquid, so you don't need any solvent, just heat it. Yeah. How the reaction goes? I mean, throughout the heterocycle synthesis, what I showed you, there must be some nitrogen source, oxygen source, or sulfur source. And nitrogen, oxygen, sulfur being the nucleophile, it will react, there will be some ketone. All the reactions, all the synthesis I just so far I taught you, the basic mechanism is that the nucleophile attacks the carbonium ion like CO. Okay, everywhere. So in that way, you can make the form of CN bond. What is the CN bond? And other carbon-carbon bond, how it will form? If you look at this, this is an acidic proton. What I will come to the mechanism, detailed mechanism. Yeah, this is an acidic proton. So what it can happen? It can attack some carbonyl or so. This is aldehyde or so to make another bond. Okay. So this is the basic principle of this synthesis. One nitrogen is a nucleophile, and this CH2 is another nucleophile. And carbonium ion is carbonyl carbon, this is a carbonyl carbon. That is the basic thing. So if you mix all four, and then you will get this dihydropyridine. Once you get the dihydropyridine, you need oxidation to make another double bond. So oxidation with the nitric acid, sulfuric acid, you get this bond. Now you have this compound is stable enough, no problem. But if you want to decarboxylate it, you can hydrolyze, it will give acid, and then heat it with calcium oxide, you can get the decarboxylation, you can get the hydrogen here. I will come to the mechanism. As I told you, the first step is Knoevenagel condensation. This is the CH2, this is minus, okay, and this is aldehyde. So first thing is like this. So you know Knoevenagel condensation. Already I taught you in the rearrangement reaction, the Knoevenagel condensation. You can get this compound. Fine. This is the unsaturated carbonyl compound. The CO, this CH2 attacks here, and then OH, you can dehydration, you can get this. Next, second molecule, that is this beta dicarbonyl compound with ammonia. With ammonia or amine, you can get the imine or like shift space. So you have got enamine. You can get this thing, nitrogen, right? O minus. Then eventually this hydrogen will get, and O minus will go. This you will get it enamine. That is the normal principle of making enamine. Any ketone with an amine, you can get an enamine. Okay. So you got in ester enamine. Okay. So one hand you have ester enamine, other hand you have this Knoevenagel product. Okay. Now these two will condense. So this is the enamine, and this is this. Ultimately, what happens is nitrogen, the lone pair is there, and this bond, carbon-carbon bond. Okay, you get one thing. Again, you have NH2 and the OH, and this is the carbonium ion. What will happen? Easily we can make this bond like this nitrogen will like this, and this ultimately it will leave. So we can like this, exactly this. So this nitrogen comes here and this keto, and you are getting OH. Then dehydration, normal, you can get this dihydropyridine. Then oxidation, you can get the normal pyridine. Okay, so that's like this is a normal pyridine. Okay, so by decarboxylation, oxidation, and decarboxylation, you can get this one. So again I'm telling you, the mechanism, all the mechanism is formation of one carbon-carbon bond, one formation of carbon-nitrogen bond. This is the pyridine. So carbon-nitrogen bond is formed by an amine, two carbonyl compound, and carbon-carbon bond is by some nucleophile going to electrophile. That is nucleophile displacement reaction. This is the two principles. Based on the two principles, all the synthetic procedures are developed. The next one I will show the same principle. So you should not have any difficulty understanding that. Clear about this? What about this synthesis? Is it clear to you? Any problem? Yes, sir. Okay. Then I will ask you to deduce another one. Okay. The same thing here from 1,5-dicarbonyl compound and ammonia. Just heat it, 1,5-dicarbonyl compound. You can easily imagine again, nitrogen is nucleophile, so it will attract here. So you are attaching NH, double bond N or NH, and that NH then, if you say some NH here, and that will attack this one. Okay. And you are getting the oxidation, you are forming this compound and then this. So here, all the carbons are this. Only thing you have to put one nitrogen, and that your base is just all set. You have nucleophile, you have carbonium ion. Nucleophile attack carbonium ion, forming OH. When it's in OH, H is here, you are getting double bond. Fine, one bond is this. And once you have NH here, this NH, then again another carbonium ion is all set. You are getting another OH, and that's OH, then again will go this, you will get this compound. So it's so simple. Mechanism is very, very simple. All mechanisms are almost the same, based on same principle. Clear enough? Okay. Now, this is 1,5-dicarbonyl compound. Extrapolation of this approach is that you are making the 1,5-dicarbonyl compound by this method. And that's also very simple. That's like your aldol or this reaction. When you have a ketone, and if you have some base in this, what can happen? You can have that anion here. Once you have the anion, then what can happen? It can react here, and this can leave. So what will happen? MeCO, CH2, this bond is formed. This bond is formed. This red line bond is formed. Okay. Once we have that, now you put NH3. The same thing. Okay. Same mechanism. This one pair, it will react here. OH. Once you have OH, this hydrogen here, it will be double bond here. And then NH, this NH will then react with this carbonium ion. Again, it's the same thing. You are getting this compound. It can go with ammonia, or it can give hydroxylamine. If you use hydroxylamine, it will be oxime. If you ammonia, you will get in one step. So you can oxime and then getting this compound. Clear enough? The same principle. Nucleophilic addition of amine or this to carbonium ion. That's only this. Other bond is already formed, so you can get this compound. Clear? Or any question? Okay, fine. Looks like everything. You are all intelligent. Yeah, fine. Again, the same. It's just on the jugglery, you can say. Now it's by the reaction of 1,3-dicarbonyl compound and enamino ester. This is enamine or ester. Enamino ester. What will happen? Just tell me what can happen here. how I will not explain the mechanism. Just you tell me what should happen here. Anyone tell me how the carbon-carbon bond will be formed and how the carbon-nitrogen bond will be formed to make the pyridine? You just tell me. Just tell me. I will. It's okay. I will understand. You tell me how that will form. Anyone? Mm-hmm. Mm-hmm. Okay. So you mean that this one and this one and this one, right? Like this? Okay. So you are getting ultimately double bond NH, okay, and you are getting this bond and this bond, this double bond will go. So it will again you can reform the double bond by dehydration. Okay. Now you have got NH, and this NH now react with this one. Okay, right? The same thing. Yeah, fine, fine. Okay. So that's okay. If you know this, just you practice it. You practice at home, you will find that really you will find pleasure. Then oh, you make the compound, you solve the mechanism. It's all same, but if you practice it by yourself, you will enjoy. You will enjoy that you can solve the mechanism. Okay. And one thing I'm telling you, whether you are making this bond fast, CN bond fast or CC bond fast doesn't matter. Because in the reaction media, no one knows which bond is formed first. We are just making jugglery and making this thing. So it's so fast that it's all the same. Maybe it's this concerted process is going in the same way. So you just do it. No, you go step by step. Okay, this is a little different. That is Boltzmann-Raj reaction. And what is that? This is again nitrogen source, that N amino ester and an acetylenic compound, acetylenic ketone. And what can happen here? The same, what I explained in the last slide, the same. Nitrogen will go and it will attack here. The same. I'm just arranging it in the same way so that you can understand clearly. Here also the same thing will happen. Your nitrogen lone pair is here, this, and this will, this. Okay? Then what happened here? You are getting double bond NH, and this bond you are making ET, and this ultimately COMe, and this. Once you have got that, again nitrogen has lone pair, and this carbonyl group. Very simple. It will attack this carbonyl group, ultimately to OH, and then to dehydration. You find that this N, all Me here, this Me, CO2 Me here, ET here, all are here, and you are making this bond. If you look at this 1, 2, 3, 4, 5, 6. So 6-member ring with nitrogen. That's pyridine. Clear? The mechanism are all based on the same thing. So in midsummer you will not get the exam, this thing, but in summer you will have. And if you have to ask to do the synthesis, you should not forget the mechanism. And you can explain by yourself, you can deduce by yourself. Because all are on the same thing. That is, nitrogen CN bond is formed by amine and carbonyl group, and CC bond is formed by some nucleophile attacked by carbanion. That's all. Clear? Okay. Now go on to synthesis. All the synthesis, just changing of the starting material, but mechanism and concept is same. Rather, concept is same. Here is guanacid synthesis. If you look at this, N-amino nitrile. This is enamine and this is nitrile. Okay, and this is again beta ketoester. This one you can enol, you can say. Okay. So here, what will happen? The same thing, same jugglery. That's the nitrogen. This OET will leave. Okay, that's the leaving group. So what you are getting? CN here, and this bond you are making Me, this double bond CMe, and then N, and this N then again attack the carbonyl will go. We are ultimately making the molecule. Clear? The same mechanism. I mean, someone told it the same mechanism. Here also the same thing with potassium carbonate and all things. And if you look at the things all set, here this will be an ion. If you have an ion, then it will react with this, this. So you are making this bond, and OH you are getting double bond. This is left with this nitrogen, it will react this, you are making this bond. So the same principle, the carbon-carbon bond formation, carbon and carbon nitrogen bond formation, carbon-carbon bond by almost like aldol reaction or nucleophilic displacement reaction, and this bond is one CN bond formation by amine. By addition, this is also nucleophilic reaction. The nucleophile is amine and carbonium is a carbonium ion. Clear? Anything new? It's okay? Clear? Okay, fine. That's fine. So your answer is okay. Now little different. That is, cycloaddition reaction already explained. And that time also I told the synthesis of pyridine by cycloaddition reaction. Here, if you have a diene and a proper dienophil with nitrogen here, that is CN. Actually, this is CN, right? If you look at a thing, this is CN. This molecule is this, right? Yeah. So I did this fashion. Yeah. So it will be 350 centigrade gas phase. It will be difficult reaction, but Diels-Alder reaction and cycloaddition reaction, you can get this now. You are making this bond, and it will come here. So you are making this bond. Normal Diels-Alder reaction, 4 plus 2. 4 plus 2. Okay. So CN will be here. And now we have to undergo oxidation to make the other double bonds. You can get this compound. This is not a very good reaction, but it's one of the method, and you can make this compound. That's the concept of cycloaddition reaction, based on the concept of cycloaddition reaction. The next one also based on this. Just if you look at a different jugglery, okay. Here you have a furan. Furan had 2 double bonds, so you can have a diene, cyclic diene. And we have double bond, that it will acrylic acid. So you have double bond here. So this is dienophil, this is diene. What will happen? So again, the same thing. If you look at this dienophil will react with this diene, forming this, and this works like a bridge. It will remain as a bridge. And this type of bridge is not very stable. So on heating, on the reaction condition, on heating, this will break. And once it will break, say on one way it will break, it will give OH. And OH say OH. Once in OH, double bond H is here, so it will double. So you get this compound. So that's a nice method. And here the yield is much better. And if you look at the thing, by the proper choice of the starting material, this reaction can be done in benzene at 70 in reflux. That means it's not like 350-degree temperature here, gas phase, difficult. But here, just with proper choice of the suitable diene and suitable dienophile in benzene, you can get a 70% yield of this product. So that's better, because you are having the different types of stable starting materials. Furan is relatively stable, this is stable, so you can do the reaction in benzene reflux condition. Okay, similarly again from furans, as I told you that time, that furan, this ring can be clipped. With ACL it's clipped. Yesterday, in last class I discussed elaborate that how that can be clipped and how we have solved the problem in our research and all the things. So here is a furan. You are treating with aqueous HCl. So you are cleaving this furan bond, O bond. What will happen? Like this. So it will be ketone here and NH2. This is NH2 already there. This is NH2 here. Okay. Once we have this compound, now platform is set. Platform is very set. The simple thing, you have nitrogen lone pair, you have carbonyl, this is a carbonium ion. That's it will work there. You will get OH, just dehydration, you can get this compound. Okay. So it's a very simple thing. That is from furans, because earlier day I told you that furan is easily available from coulter. So furan is cheaper than pyridine, furan is cheaper than pyrrole. So furan can be used as starting material for making pyrrole, for making pyridine also. Clear? This thing? Is it okay? Okay. Okay. Little different, but the chemistry is again same. This is propargylamine. This is triple bond. This is called propargylamine, and this is cyclooctanol. We are making a fused pyridine. So you can easily understand that you have NH2 and O. So what will happen? Very simple thing. Okay. So this bond you are making, and because OH is here and double bond is there, so you are making a double bond here, and OH will leave. Okay, fine. Once you have this compound, this is an intermediate. Once you have this compound, what can happen again? Still you have lone pair, this, this, this. That's what happened, and you are making this compound. So this compound is with some catalyst. You need some sodic auric chloride, gold catalyst, some ethanol that goes within 78 degree. You can get this compound. So basic mechanism is same, that formation of carbon nitrogen bond and carbon carbon bond, but in different technique, not aldol type reaction. It's you can say some addition type reaction. This is some addition type reaction. Okay. Yeah. That's yeah, okay. That's from our lab. We developed also another method for this. We have some contribution in heterocyclic synthesis like pyridine. I showed you our contribution for pyrrole, for making furan, now for making pyridine. We have also some paper from quinoline. But anyway, so this is for pyridine. And that's again in a multi-component reaction. The aldehyde, this is melanonitrile and thiol. Okay, and we are in the same ionic liquid. I already explained that. This is butyl, methyl, imidazolium hydroxide, and ethanol. And one of the things you will notice the difference of our method is room temperature. If you look at the things, all these methods, I'm coming 78 degree. This is of 0 degree. Okay, reflux 350. So most of the methods are done in high temperature, but our method was done at room temperature. And this is the base, with the base developed by us, the butyl, methyl, imidazolium hydroxide. In ethanol, you can get this compound. And if you look at this pyrrole, pyridine, if you look at this pyridine, all positions are substituted. 1, 2, 3, 4, 5. The other methods, you will not get all positions substituted in one step. So this is highly substituted. It was a highly substituted pyridine. So all 5 positions are substituted. You can make this compound in one step. Okay, the mechanism I'm showing you. First thing again, the Novenigal reaction. The same principle. You have aldehyde and melanonitrile. So this will be your anion. This anion react with this. So you are getting the dehydration. You are getting R, CH, carbon, CN. This is the simple Novenigal product. Take this Novenigal product and take another melanonitrile and thiol. What will happen? Just look at the same molecule, we wrote it like this. C triple bond N, cyanide. Then this C. Then C cyanide. Then double bond R. This molecule was written like this. And this molecule, if you look at this, one anion here, the melanonitrile is this anion, CN, CN. This is melanonitrile. What will happen? The carbon bond will form now. This, and also in another step you can get this bond. So you are making carbon-carbon bond and carbon-nitrogen bond. So you are getting the pyridine molecule. One SR is here, that is the nucleophile. CN is here, R is here, whatever R you take, methyl, nitrile is here, and double bond NH is here, and that can be converted to NH2. This with the base and this, you can get this compound, and then just dehydrogenation, you can get this molecule. So if you look at the things, that is a unique molecule, a pyridine ring with NH2, which can be manipulated. Very good functional group. Nitrile, another very good functional group which can be reduced to CH2NH2, which can be hydrolyzed to carboxylic acid, which can be hydrolyzed to CHO. So this CN also the same thing. And SR the thiol. Thiol is a good nucleophile, it can be elaborated. So this molecule is very, I say, valuable precursor. It's a valuable compound in the way that it has all the functionalities in the molecule which can be manipulated, which can be transformed to other groups. Okay. Anything? Any query on this mechanism and the synthesis? The mechanism based, no sir, fine. So if you are given a question on that, can you write it? Are you sure? Okay, okay, then very good. Okay. Yeah, because that's one of the this method, not because of our method, but this compound is one of the best method for making pyrrole because it can give you all 5 substituted pyrrole, which other methods cannot give. That's one of the things. Yeah. Okay, and that one thing I'm just telling you that this work was done by a summer project student. She came from IIT Madras, and within 3 months, summer project student, she completed the work. Of course, she associated with some senior person. So those, I mean, who are doing the summer project somewhere in this, try to do the work, I mean, very well so that you can put more labor. You can also have a paper. Many students in my group who came from summer project got very good paper. And that girl got PhD from Taiwan, and now she's a faculty. And other person is Arjana, just he is a scientist in ISCB next door. So, I mean, what I'm telling that if you do good work, you will be rewarded someday. Anyway, now reactivity of pyridine. Pyridine, as already I mentioned, that pyridine is electron deficient. And because we have this nitrogen and the nitrogen is lone pair, it is basic. Basically, it's a basic molecule, and pyridine is used as a regular base in organic synthesis lab. I mean, we use, pyridine as a base and a solvent in many reactions. Okay. And because of this lone pair, if you use any electrophile, what will happen? That electrophile first react with this nitrogen. If you use the HCl, what will happen? It will form the salt, chloro salt or HCl salt. If you use any acid, sulfuric acid, anything, this is a base. So base react with sulfuric acid or any acid to get the salt. You will get the salt. That is the basic reaction. Now, if you have any electrophile, what can happen? First thing will be this. That the electrophilic addition is difficult because it's already electron deficient. If it is electron deficient, it cannot attack an electrophile. So electrophilic substitution is very difficult in pyridine. I will explain. And when it is possible, if you pump out some electron, it is electron deficient. So if you pump some electron on the ring, then you can do it. How you can do it? If we put some electron donating group, if you put some electron donating group here, then only then you can have some electrophilic substitution. Clear? Okay. Then reduction, it's a nutshell, is the reactivity of pyridine, but I will explain. You can reduce the whole ring by hydrogenation with platinum. You can do that. Okay. And if you have, say, if you put some RH, means the radical substitution. Radical reaction is different. I will show that also. If you have put a radical can easily attack there. You can get from this compound. And nucleophilic substitution is very familiar because already the ring is electron deficient. If the ring is electron deficient, any nucleophile can attack here. And usually the nucleophile goes to 2 position. Nucleophile goes to 2 position because nitrogen is here. So that is partial positive character. Right? This double bond nitrogen will take out. So this will be partially positive character. This position or 4th position. So here the nucleophilic substitution usually occurs at 2 position. This is this. Okay? And if you use any other electrophile, as I already mentioned, that you will go to nitrogen. Or if you use any methyl iodide, it will go to this N-methyl. And this is important. I will discuss on that. That is N-oxide. If you treat pyridine with any peracid, it will go to N-oxide. And pyridine N-oxide is very important for reaction. I will discuss that. And already I discussed some in during nucleophilic and electrophilic substitution of aromatic rings. But I will discuss again that pyridine N-oxide is very important intermediate. So your concept should be clear on that. That what I will teach you, just an elaboration of this or demonstration of this. So, did you understand all the reactivity and the reactive character of pyridine? Any question on that? Yes. 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 Palladium. No, no, no. Zinc cannot. Okay. I'm telling you again. This is a hydrogenation reaction. Okay. So hydrogenation, how it goes? When you use, usually palladium is a good thing, good metal. Palladium or platinum, they are used for hydrogenation. Platinum is very, very expensive, and platinum is much reactive also. So what happens when you use some catalyst, palladium catalyst, palladium first absorbs hydrogen. We have hydrogen set up in the organic chemistry lab. And all the faculty, they have the setup. We is regularly used in organic chemistry lab. So what is that? When you use some put some palladium in the hydrogenation, so hydrogen will blow through palladium. Palladium will absorb hydrogen on its surface. And when you have the reactant, any substance, anything, now the palladium surface will dissolve hydrogen slowly, and that hydrogen will be absorbed by the molecule. This is the basic principle of hydrogenation. Okay. Now, the question is, why palladium and platinum? What is the difference? Palladium absorbs the hydrogen and dissolves also. I mean, dissolves also very quickly, and quickly or relatively fast. But platinum keeps it for some time. So platinum supplies the hydrogen to this, and platinum also makes some complex with this double bond and all that. Palladium also does it. Platinum also can do that. And while doing that, then one way the metal makes some complex with this, and other way the hydrogen is now coming from this side, say, and metal will be dissolved. Okay, so it's going like this, or rather, say, this is platinum or palladium, and what is that double bond? So this double bond first forms the complex like this. Okay. Now hydrogen comes this from palladium surface. The hydrogen comes from this surface and slowly reduces this. This is the mechanism. So the platinum characteristic is different from palladium. Palladium cannot go all to the put pyridine. It can go with dihydropyridine, something like that. But platinum can give rise to completely pyridine. That is because of these characteristics of platinum. And platinum usually we don't use because it's very, very expensive, unless it is specifically required. Clear? Yeah. Uh, some extent you can do it. I will teach that also. I will put in this after a few minutes. You'll find it today or next class. Yeah, you will find it. Yeah, sodium borohydride, lithium iodide can also reduce it, not fully to pyridine. It will be dihydro or tetrahydro, something like that. I will come to that. It's possible. Because one thing is that because C double bond N can be reduced by reducing agents, normal reducing agents. Like you have not the cyclic, you have some C double bond N or even C triple bond N. That can be reduced with any reducing agent. Sodium borohydride or lithium aluminum hydride. That can be done. LH. So that can be done because C double bond N. But even this is cyclic, this is acyclic, but can be done in some way. I will come to that. Okay? Okay. Now, electrophilic substitution, as I told you, that is very difficult, and we mentioned that the electrophilic substitution, because nitrogen is there, always the electrophile comes, nitrogen will catch. Nitrogen is much more nucleophilic because it's a lone pair, so any electrophile will come, first will go there. And after that, it can have some electrophilic substitution, but depending upon the condition I told you. And this reaction is unfavorable, so usually pyridine does not undergo electrophilic substitution. Clear? Unsubstituted pyridine usually does not undergo electrophilic substitution. Only on special condition, on special reaction condition, they are compelled to go the electrophilic substitution. And reason is that pyridine is electron deficient. It does not have electron deficiency. So how can I attack another electrophile? Clear? Okay? Yeah, okay. Okay. Nitration. I'm telling electrophilic substance in what condition? Already I told you, you have to pump electron to pyridine ring. So if you put two methyl group, which are electron donating group, these presence of these two methyl now make the pyridine ring somewhat electron rich, and then you can make the electrophilic nitration. Say this condition, okay. This is now this. So you can make first you make the N nitro is fine, yeah. Usually, what are the any electrophile will first go to N, so you get N nitro. But if you have the N nitro, then you can have this condition potassium nitrate and sulfuric acid, and then nitrate will come here, so you can get this nitro compound. And if you look at the thing, okay, I'm telling you, as I told you, pyridine itself does not undergo electrophilic substitution under usual condition. Here is one example that this is unsubstituted pyridine, so it should not go, it should not undergo any electrophilic substitution. So what is being done? Potassium nitrate, concentrated sulfuric acid, 300-degree temperature, 24 hours, you are getting only 6% of this product. This is an ideal example to support my view that pyridine itself does not undergo electrophilic substitution. Which condition is good? Either you have pumped electron like electron withdrawal group, I will come to that also. And here also first it goes to that, then it can go to 4 or 3 position. And here if you have no substitution, simple unsifted, in this harsh condition, putting in this highly harsh condition, you are getting only 6% nitration. You can imagine now why you can explain that pyridine itself does not undergo electron substitution because it's already electron deficient. So nitric acid, constant sulfuric acid, 300-degree temperature, 24-hour time. Even then you are getting only 6%. Yeah. But look at this. You have to pump in some electron, so you have two Cl group. That's also electron donating group in this case, and so you are getting NO2. So here this carbonium, this is the electrophile. So what you can get is now again look like this, this carbonium ion, or you can get this one like this. So you are getting 3 positions. You are getting NO2. Okay, this lone peridot here, here, and this position. Now this comes to here. You can get 3 nitrochlorine because 2 chlorines are present. Similarly, the N-amination of pyridine. If you have pyridine, you are putting some amine group. First, it goes to this NH2. Here also NH2, 1 ammonium pyridine. Here also, if you put this compound, it gives tosyl group here. So all the things initially go to nitrogen because this is the strong thing. This is the rich person here. In pyridine ring, nitrogen is much richer in electron density than all carbon positions. So any electrophile will go to nitrogen first, and that's what happens. And then it may go in the carbon or may not go, depending upon the condition of this. So these examples show the amination goes to nitro, or even nitration goes to nitro. In certain condition, it can go to carbon nitrogen. Clear? Sure. Substitution, right. Both. Mainly because it has a triple, all aromatic character, only resonance will be stronger here than inductive effect. But inductive effect can also be operative. Sure, it will be the resultant effect of both inductive and resonance. And resonance effect is strong because it get a long resonance stabilization. Clear? If you put OMe, that's very good is OMe. I will come to that. If you can put OMe, that will be the best bet for electrophilic substitution. Possibly I have some example. Let's see. Yeah. Sulfonation. Again, the same thing. If you have unsubstituted pyridine, it goes to nitrogen. Heat and this will go this. Okay, this will dissolve. If you have again pyridine, look at the reaction again. You are getting SOCl2, room temperature 3 days. Even if that, you are getting nitrosulfonation after 3 days, 40%. Now we have SOCl. Here one thing, if you look another thing here, when this nitrogen of pyridine is attached with some other group, the effect of nitrogen is much reduced. So nitrogen is positive charge here. It cannot pull the electron from the ring. So this ring is now somewhat electron rich than compared to unsubstituted pyridine now. So what can happen now? So it can undergo electrophilic substitution because the ring is now relatively electron rich compared to that, because this electron of nitrogen, two lone pair electron now bound with SOCl. Now if you put some another molecule of pyridine, this now can work as a nucleophile. So this nitrogen now, this pyridine nitrogen can react here and give like this. So you can have this molecule, then we can remove this part, you can get this SO3Na. Okay. So in that way you can get some molecule like this. Okay, the electrophilic substituted pyridine here. Yes, okay, that is the ideal. What I'm looking for. If you have a OMe, that's an ideal case for giving or pushing electron to the ring. Is a very good electron donating group. So if you put bromine and sodium acetate acetic acid at this condition at 10 degrees centigrade, you can have bromination at the para position. You can have bromination at the para position of OMe. That is electrophilic substitution when you have an electron donating group present in the pyridine. The same thing here, if you have a OH electron donating, you can be electron donating here, and then you can have sodium iodide. You can have this ortho position here. This is para position. This is ortho position. And here also you can have formaldehyde, and there's a Mannich reaction, and at the 2 position you can get Mannich reagent CH2NMe2. Okay. So it goes either the 2 position or the para position of this here. Here also, this thing, another thing I already mentioned because of this thing, aromaticity and aromatic substitution. For pyridine molecule, this is a very stable thing. If you have a pyridine, this thing easily tautomerizes to this thing. And this thing is much stable. And that's why when I explained that if you treat that with methyl iodide, you cannot get OMe. You cannot do methylation with this OH because it tautomerizes this, and mainly say 80% remains here and 20% remain in this stage. So this compound is quite stable and reactive. If we have this pyridone, this is called N-methyl pyridone. In that case, if you halogenate it with chlorine in this, you can easily halogenate it here now. You can get this 3,5 halogenation with this. Again, if you take this pyridone, in the 2 pyridone, this 4 pyridone, you can do the nitration here. Because this is different from pyridine. Now, the ring is not that electron deficient like pyridine. We have CO, electron withdrawing group, right? Here also CO is electron withdrawing group. CO is electron withdrawing group and NH is there, and this aromatic character is somewhat lost. And in this case, what can happen? That you can have some electrophilic substitution at this molecule. It is pumped like this. Nitrogen, because electron withdrawing group present here, so it comes this, and this one supplies electron at the same time. This one now become electron rich, and it can react with nitric acid to giving this nitro compound. Clear? But not possible with pyridine. It is possible with pyridone. It's okay? Yeah. Pyridone is not completely aromatic. No. Yeah, I mean, at some aromatic character, but we cannot call it aromatic. No, definitely not. Tautomerism, exactly. It's a ketoenol tautomerism, something like that. Right, exactly. Yeah, but it remains on that. Yeah. Okay. I give some more of pyridone chemistry, because with pyridone you can give some substitution reaction. With the same pyridone, if you take with this acylation, you can get OH-3. And also, if you have this molecule, and this is now, if you look at this now again, with this pyridone, when you put the acylation, you are getting the pyridine, again coming back to pyridine. Once you get that, if you put some electrophilic reagent, what will happen? This goes to nitrogen, looks like that. And it comes to that, then this OH-3 easily, it clips, you can get the pyridone. Clear? If you take this pyridone and the phosphorus pentachloride or POCl3, the chlorinating agent, the first thing you will get OPCl3 here. Okay, that's a nucleophilic substitution. The chlorine will attack here. This will go. You can get this, and then it will leave. You can get this thing. Okay. So basically it's a nucleophilic substitution. It's a nucleophilic substitution on this, on pyridine, but it's going to pyridone. Again, it's 4-pyridone, and this, it will be a nucleophile here, this nitrogen, so it will react here, you can get this compound. So with the help of pyridone, you can get some pyridine substituted molecule. What I'm telling that, you cannot get 2-chloropyridine from pyridine, but you can get 2-chloropyridine from pyridone. That's what I mean. And from pyridine to pyridone is very easy to get. So here, so again, by the help of pyridone, you can get 4 substituted pyridine. So that's the chemistry of pyridone. With the help of pyridone, you can have some substitution at the pyridine. Clear? Okay. Sure. Sure, go ahead. Yeah. Yeah. No. Both the same. OPOCl3 is not a catalyst. POCl3 reacts with this, give OPOCl3. OH is there. So OPOCl3. And that's a very good leaving group. Now Cl5, this is the chlorinating agent. Okay. The PCl5 is a chlorinating agent. PCl5, okay, I'm telling you from higher secondary class. With PCl5, you can do chlorination of many alcohol and all the things. That time you are using PCl5 or PCl3, right? Phosphorus trichloride or phosphorus, yes, yeah. But POCl3 is not the chlorinating agent. POCl3 is used here to make this OPCl2. That's a good leaving group. That's why you are using it, this one. Clear? Yeah. Like if you have any molecule, say not cyclohexane or whatever, if you have OH is not a good leaving group. Either you have to make it with proton, the acid OH2, or you have to make OHO3 or something like that, or O, say PCl5, PCl4, something like that, or OLCl4. So in that way, that will be a leaving group. So in that way, OPOCl2, that's a good leaving group. Now coming nucleophilic substitution, which is very common for pyridine, because pyridine is electron deficient. So normal, it's a normal thing. If you have, and the basic thing of nucleophilic substitution is what? You should have a substitution. You should have a leaving group in the molecule, like in benzene also. You should have a leaving group in the molecule, and then nucleophile attacks there, and the group is left. Based on the same principle, we have pyridine, 2-halopyridine, and now we have any nucleophile. Nucleophile will react here, initial nitrogen here, then it will fire back, and you are getting the halogen will be left out. You will get the two substituted nucleophile here. The same thing here. If you have N-butyl here and you are using N-butyl lithium, so what will happen? You will lithium. First, what is the you are using a butyl lithium. So first thing lithium will be nitrogen. So you are getting this lithium, and then you are getting butyl lithium. So you can get nucleophilic substitution here. So nitrogen is here, and then this will attack here. You will get this one. So you are then lithium elimination of LiH. You can get this molecule. So all these are nucleophilic substitution of pyridine at the 2 position. 2 position is more favored position, and here also if you have PHLi, you can get in the 2 position, you can get this compound. Okay, so these are all nucleophile. This is nucleophile PHLi, Li plus, PH minus. Butyl lithium, Li plus. This is a metal. So butyl is nucleophile, PH is nucleophile. So this is nucleophile. In place of nucleophile, you are putting PH or butyl. So you are getting this one. Okay. Okay, I'm telling you again. What is this butyl is nucleophile or electrophile? This butyl is electrophile because this is a negative charge. Okay, fine. So that's another concept. Is to make your concept clear. If someone asks you that in what is the nature of an alkyl group, if someone like vague question like that, you should ask him in one condition, that the same methyl can be a nucleophile, the same methyl can be an electrophile, it depending upon the condition. If you put CH3Br, it's an electrophile. If you put CH3Li, then CH3 nucleophile. That concept you should have clear. When you have a metal, metal is a positive charge, so the other part will be negative. When you have a halo, halo is a more electronegative. So halo will be negative, but that alkyl will be positive. Clear? Okay, this concept you need it. I mean, really, if you remember all the things, you will enjoy chemistry. Okay. Now amination, but we are discussing nucleophilic amination, nucleophilic substitution reaction. So you need a nucleophile. You have pyridine. We are putting a base sodium nitrite, and this is the aminating reagent. So what you are getting is there N plus this, and then you are getting this NH2 like this. Okay, and that can tautomerize like this. Okay, to give this NH2. Okay, those at the 2 position, again amination at the 2 position. And if you have NO2, if you have this pyridine, 3-nitropyridine, so it is much better. This is electron withdrawing group. You are putting an electron withdrawing group to pyridine. So the nucleophilic substitution is expected to be much faster, right? Pyridine itself is electron withdrawing ring. You are putting another NO2, means electron making more electron deficient. If it is more electron deficient, nucleophilic reaction will be much better. You are using this nucleophile here with zinc chloride room temperature reaction. What you are getting here, the same this NO2 is here, and then so you are getting this again 2 position. This NH2 will attack at the 2 position like this. So what NH, this molecule, this, and don't this is the only better leaving group, nothing else. It's an aminating reagent. NH2 is the nucleophile, and this is the better leaving group, nothing else. Okay. If you put NH2OH, that will not be better leaving group. But NH2DS triazole is a much better leaving group. So this nucleophile now reacts with 2 position. You can get this one here. Okay. Now this hydrogen will leave double bond NH, and this will be one double bond NH. Then it will on reduction or on protonation you can get NH2. So you are putting an NH2 at the 2 position. Again, you look at the para position of NO2, but at the 2 position of N. At the 2 position of N is more important. So in pyridine, the 2 positions, all the same, 2 or 5. The 2 position is most susceptible for energetically more favorable for nucleophilic substitution. Everywhere you are find that is 2 position. Clear? Any question on that? Clear? Fine. The same thing. Okay, another amination, you're putting it here. Okay, if you have a different, just amination, different kind. If you have a dibromo and aqueous ammonia, and at this condition, you can, this NH2 now is a nucleophile, it can attack here in living group. So it's a different kind. Here also the same thing. If you put a Br here and same ammonia copper sulfate, so this, okay, you are getting this because your living group there, so you can use normal nucleophilic displacement, reaction. Here there are the different concepts. Again, I'm coming. Already you know benzene. Okay, I'm giving one example. In pyridine ring also you can have benzene same thing. You can have benzene. This is arine. Definitely it's not benzene. The arine. Here, if you look at this concept here, the 3-bromo pyridine. This is a nucleophile. You are putting the same sodamide, the same strong base, tertiary. When you have a sodamide, there is a possibility like benzene ring, there is a formation of benzene. That's what happened. But it's not very common. It sometimes happens at this condition. You have to put this condition and this. So you have put this now benzene. Once you have that benzene, this is a nucleophile. Okay. So this nucleophile, nitrogen nucleophile, it can attack on this position or this attack from this position. So in principle, you are supposed to get 2 products, and that's what you got. And that proves the benzene concept. Again, I'm telling you that when the benzene, I this explained it in details, that how the benzene concept came and why the things. When the chemist got 2 products, then this concept came. If it is a normal nucleophilic, this is 1, right? Like this. This is a normal nucleophilic displacement. So you are getting this, you are getting this. Okay. You can ask that why is not benzene being formed here? Because of the condition. This is the aqueous ammonia between copper sulfate and this. So this position benzene is not formed. This nucleophilic displacement is much favored. But here the condition is that you are getting the benzene. And once you get the benzene, there is a possibility of getting 2 products. Okay. But instead of 2 products, if you get only 1 product, then this idea will not come. Then there is this normal, then this only this product, not this one. If not this one, if we get only this product, then it's a normal nucleophilic displacement. That nitrogen, it goes there, when bromine is left out, you are getting this thing. Okay, this is the normal nucleophilic displacement reaction. But when you are getting a mixture of 2 products, then that possibility of benzene comes, and it establishes that benzene is being formed. Otherwise, you cannot get 2 products, mixture of 2 products. Is it clear? That's a very, very good thing. Is it clear to you? Just tell me. Clear. This question, yeah. Copper sulfate, what happened now? Again, already I mean this Cu, this form is like, if you, when you have metal in general, if you have a Br, treat with any metal, it will be okay. It will be this M copper bromide, M Br or whatever thing. Once you have this position is now much reactive because this bond is much weak. So any nucleophile, any damn nucleophile now can easily attack there. It will be better living group now. Clear? Exactly, the same. Not this principle. If you look at the chemistry, it's all on that forming the carbon metal bond. Ignite is what? Carbon metal bond, right? So why carbon metal bond? When you have a carbon metal bromide bond, then that MgBr will make that position more reactive because that bond is weak now. When it was CBr, the strength was much more, but when you put in between on metal, Mg, then that bond is weak now. So what happens here? When you put a metal, you bond is weak. Now any nucleophile can react on this thing. That's why it does not undergo benzene. Clear enough? Is that interesting? Okay. Okay. Go deep into the chemistry, you will find really pleasure. Okay, fine. That's all right. So you need lamination. Okay. Okay. The silidation. The same thing if you have a normal pyridine, in this condition here, the Remi3 is HMPA, and with this reagent you can have it's an intermediate. You can have some silylation here, and that can have this undergo tautomerization, and ultimately you can get this 19 silylation here. You can get it. So that's again it's a nucleophilic nucleophilic reaction, not electrophilic. So benzene pyridine ring is electron deficient. So with a strong reagent like that, you can have this silylation. Similarly, thiolation also the same thing. If you have an if you have this compound here, that's 2-chloropyridine. 2-chloropyridine all means you have to, this is a living group. So whatever you have, NaSH or SM, whatever that is normal things, already this nucleophile in the back here, this will go. Not in simple case, it will go less like this. So initially it will go like this, and then backfire, and then this go. That's the correct mechanism. But for simplicity, I'm showing in that. So it will be thiolation. The same thing with this, you can get ON. If you have sodium methoxide, this is the nucleophile. So you can get alkoxylation. So thiolation, alkoxylation, all is nucleophilic substitution reaction on pyridine ring. So in pyridine ring, if you have a living group, that is more facile, and on the living group, that position will be attacked definitely. But if you don't have any living group, only pyridine, that in that case also the reaction occurs, usually at the 2 position or at the 4th position, right? That is the thing that you keep that in mind. Clear? Okay. I will come with another nucleophile and stop here. Reaction with other carbon nucleophile. I show you other carbon nucleophile. And the same thing, if you have CN and methyl. So what in presence of a base, what can be the nucleophile? Easily you can find that this, because this hydrogen is the most acidic hydrogen. So this is the nucleophile here. The reaction is same. This is the nucleophile here. And pyridine you have 2 bromo, right? What can happen? Same displacement reaction, because this you can get this compound. Very easy, same thing. Okay. In this case also here you have again nitro and Cl, ideal. Nitro is electron withdrawing, so it is making the ring more electron deficient, and you have a living group here. Very good, ideal thing. So any nucleophile will now react. You have NMe, so you have NMe and double bond this molecule. This is some indole molecule, and here very interesting reaction. If you look at these things, if you remember in indole, I told you that 3 position is the most reactive position, and 3 substitution occurs in 3 position. Here this example is that nitrogen is here. This is the 3 position now. So this reaction, look at this reaction. This is the pyridine, and 3 position of the indole now reacts here. This bond is from the 3 position, because in indole 3 position is the most vulnerable position for as a nucleophile. So here this position is negative charge is formed. This negative charge now nucleophile now reacts here. This is a very important reaction. Clear? LCl3 and this. Did you understand or not? Okay, fine. So I will stop here today, because always you will tell that heavy and these things. Okay, I will go rather slow, but if you can understand, it's fine. Okay. And to announcement, tomorrow there will be a class test on rearrangement reaction, and it will be an offline class test. So you will come in the class tutorial, the TA Shobhan will give you the question paper, and you will write it there, and you will take up the question your answer scripts. Okay, so that will be again official. And about the mid-sem, okay, we have been asked to set the question paper, so we'll very soon we will submit the question paper. And the mid-sem, as usual, the TA, I will ask the TA, and he will take the question paper and he will conduct the examination. But I will be online all the time. So my request to you that if possible, or I am requesting you, all of you, just like this lecture, you will keep your cam on, keep it mute, microphone off, but keep your cam on, video on, so that I can see all of you. I can also invigilate online, and plus someone will be there. Okay. So on the mid-sem, the date is not yet announced. When the date is announced, you will keep your cam on. Okay, is that possible or not possible? Okay, okay. It's my request. It's not
We
official.
have to
But
we
again,
have to give the medicine offline or online.
offline, offline, completely offline.
Then sir, how we are going to on our camera? Like I didn't understand. Like,
If it's a difficult, then it's no. It's okay. It's not official. I'm not telling you officially. I'm telling you that okay. If you have any question or anything, I can then explain. Say if you have some problem in any question that okay, this is not in the syllabus or something like that, that I can someone will be there, but I can change it. I can give my comments and all the things. Only for that I'm telling you. But it will be offline. But what's the problem? If you are offline, you are giving that time, but you have I don't know. You have camera or all the things or not? In the classroom, it's not possible, right? Okay, I mean, think of it. If it is possible, it's fine. I will take another class on Monday, so no problem. I will discuss that. But if it's not, I'm not insisting on. Or again, I'm telling you, it's not an official, say, advice or official. I'm taking you that if you have any problem or anything, so that I can solve it immediately. Otherwise, someone can tell you, or if possible, someone can call me. No problem. Okay. Go ahead. If any question or something like that, then someone can call me. I can change it, or someone can change it also. I will authorize him, but it will be offline, completely offline. But it's okay, fine, no problem. Okay then. Okay, that's okay then. So by today, and we'll meet on Monday. Okay, the rest of the pyridine and other reactions. How far I go is okay. Okay, and try to do better in your next exam. I'm really not very happy with the performance of the exam, other two exams. So that's my request to make me happy. You have already class assignment on the rearrangement reaction. Again, I'm getting another rearrangement reaction on class test. So you should be doing much better here. Okay. Okay, do it. He will give you the question papers and all the things. I have a question paper approved by me, so no problem. The questions are not very difficult, but you have to be attentive. You have to be attentive, and you have to read carefully the rearrangement lecture note and also the rearrangement textbook or see. You'll find that. Okay then, it's all right. Okay, bye.